have a slide on that, yes. But yeah, you mean the gravitational.
Massimo Elia from the University of Pisa, and he will be talking about the theta dependence of QCD and QCD-like theories. Please, Massimo, the floor is yours.
Okay, good morning to everybody. Let me start by thanking the organizers and saying that I'm really sorry I cannot be there in person. I've been running a workshop there at ACT Star a few months ago, and I know perfectly that being there in person is a completely different experience. It is always a different experience, but especially at ACT Star, where you can really enjoy being there in person. So I'm sorry, and but nevertheless, I'm happy to be present at least in remote mode. So in my talk, we will go actually from experiment back to theory, and I will make a review about things that we know about theta dependence in QCD and QCD-like theories. So this is the outline of my talk. Actually, the number of things that we know is that we would like to know is very large. So I will restrict myself to a few specific topics. So I will start by review about the available predictions that we have on dependence on the topological theta parameter in the QCD and more specifically in Yang-Mills theories. Then I will briefly review the main issues that we have to face when we try to study theta dependence from lattice QCD simulations. And then I will focus on results obtained not for QCD, but for pure Yang-Mills theories, for SUN pure gauge theories. There will be a talk on Friday by Claudio Bonanno focusing instead on the issues related to full QCD simulations. So basically the main results that I will discuss are how theta dependence changes across the various phases that we can find in pure gauge theories, and also how the phase diagram itself is influenced by the topological theta parameter. So let me start by briefly review how theta dependence emerges in QCD. So we know that most of the non-perturbative properties of strong interactions are actually related to the presence in the topology of configurations in the path integral formulations of QCD, which have a non-trivial topology. So basically, when one considers the path integral formulation, gauge configurations divide into non-trivial homotopy classes, which are labeled by an integer winding number, which is usually called the topological charge. So the topological charge density can be shown to be a total derivative as in the following. It is related to the sort of scalar product of the chromoelectric and the chromomagnetic fields. So for this reason, it is CP0. So since it is a total derivative from a classical point of view, it would have no effect on the theory, but quantum effects make it become a relevant quantity. And so the global topology makes the issue non-trivial. So the homotopy group that we know for SU3 and for SUN gauge theory is the same that we have for SU2. It is the pi 3 of SU2, which is the set of relative integer numbers. So since GG dual, so the topological charge density is a normalizable operator, it is possible to add it to the standard QCD Lagrangian, and the coupling to it is a possible new parameter of the theory. Since the topological charge is an integer number, it is an angle-like parameter. It can be considered as an angle, so it is usually called the theta angle. And let me say that one could add this parameter also in abelian theories like QED, Now, the non-trivial dependence on this parameter theta emerges in non-abelian theories because of the existence of configurations which have a non-trivial topology, but at the same time have a finite action and a non-trivial topological winding number. So these are the classical solutions known as instantons or ante-instantons. So we actually know that the theta parameter is small from experimental bounds. But in any case, theta dependence is related to many essential aspects of strong interactions that I will discuss and that will be discussed in this workshop, and also for beyond the standard model physics. From the point of view of numerical computations, of course, the fact that theta appears as a complex factor in the path integral makes it difficult to study directly its influence on the on QCD, because we have a sign problem. So it is not possible to interpret the path integral weight as a probability distribution. This is the same problem which emerges in many situations and which makes direct numerical investigation unfeasible. So what is the standard way to study theta dependence in lattice simulations? The standard way is to consider a Taylor expansion of the free energy density around theta equals 0. Now, if you write down the Taylor expansion of the free energy density, well, first of all, it must be an even function, because we have the topological charge is CP odd operator. So since the theory theta equals 0 is CP even, the Taylor expansion must contain only even terms. And it is easy to prove by just by working on the path integral defined here, that the Taylor expansion coefficients are related to the cumulants of the topological charge distribution computed at theta equals 0. So basically, you can write down the following parameterization for the dependence of the free energy density on theta. This is a standard way to parameterize the coefficients, so to factor the quadratic dependence, which is expressed usually in terms of the topological susceptibility, chi, and then to parameterize the corrections to the purely quadratic dependence on these coefficients, which are known as B2, B4. So these coefficients B2, B4 are related to the higher order cumulants. So in the infinite volume limit, basically you expect that the quadratic term, which is related to the Gaussian-like fluctuations, is dominant, but the corrections are relevant, as I will show you, since they permit to the disentangle between different kind of theta dependence in the different phases of Yang-Mills. Now, of course, the essential quantity appearing here is the distribution in the winding number, this probability distribution P of Q, and this is a inherently non-perturbative property of Yang-Mills theory. So a lattice investigation is the ideal first principle approach to directly compute this distribution, and from there to compute all the cumulants which are needed to obtain this Taylor expansion. So please, if you have questions, interrupt me at any time. Now, an essential aspect that comes in full QCD when one considers the theory including dynamical fermions is that dynamical fermions enter the game in a non-trivial way. And this is basically because of the Atiyah-Singer index theorem, which says that the winding number, topological charge, which starts as a property of gauge fields only, can be related to the spectrum of the Dirac operator, and in particular, it is equal to the difference between the number of right-handed and left-handed zero modes of the Dirac operator. At the same time, this fact is important to understand how theta dependence is expected to be in through QCD with light fermions, as I will discuss briefly. And also it gives us a different way to measure topology from lattice QCD simulations. I mean, topology can be measured either by looking at the gauge fields using the definition, the starting definition of Q, or by looking at the spectrum of the Dirac operator, so by looking at the zero modes of the Dirac operator. And well, the content of the index theorem is basically related also to the axial anomaly, saying that the divergence of the U1 axial current is proportional to the topological charge density. And using these facts, it is possible to prove that an axial rotation on the fermion fields can change theta. It can actually move the theta parameter from the gauge field sector to the quark sector. And this is important to make predictions about theta dependence in QCD with light fermions in this way. So indeed, we may consider QCD with massless quarks. It is possible that theta dependence disappears completely. This is because theta can be freely changed in this case. So we can move theta to the mass term, but the mass term is not there. So theta disappears completely. And there is another way to understand this fact from an intuitive point of view. When one considers the QCD with dynamical fermions, the path integral is modified by the appearance of the fermion determinant, which takes into account the contribution from dynamical fermions. And now the fact is that when we have zero modes for the Dirac operator, which is what happens when we have a non-trivial topology in the gauge fields, then because we have also massless quarks, the determinant vanishes. So in the presence of massless quarks, gauge field configurations with non-trivial topology are completely suppressed out of the path integral of the theory. And so basically we have that the topological charge distribution is exactly zero for a non-zero Q. Now, this is not the case when we have quarks with finite mass, which is the physical case. But also in this case, if the quarks are light, since we can move the theta parameter from the gauge field sector to the quark mass term, it means that we can make use of all the tools that we can use in a theory with light masses, like chiral perturbation theory, to make predictions about theta dependence also in this case. So now I will go to discuss what are the analytical predictions available for theta dependence. As I said, theta is experimentally a very small parameter, and actually the experiments on the electric dipole of the neutron set this bound. So one question is, why do we bother about this theta dependence at all? Well, there are several answers to this question. First of all, theta dependence enters various phenomenological aspects of hadron physics, like the Witten-Veneziano mechanism, which connects the topological susceptibility computed at in the pure gauge theory in the limit of a large number of colors to the mass of the eta prime meson. And the prediction coming from this Witten-Veneziano mechanism is that the topological susceptibility for pure Young mills in the large n limit, so in the limit of a number of colors going to infinity, is expected to be 180 MeV to the fourth power. And I will directly confront this prediction with lattice simulations in the following. From a purely theoretical point of view, there is a rich interplay between theta dependence and phase structure of Young-Mills theories that I will discuss in the following. And then there is, of course, the strong CP problem, why theta is so close to 0. We know that a possible mechanism is the Peccei-Quinn mechanism, which invokes the existence of axions, which are also popular dark matter candidates. And so this issue is particularly important, but this will be discussed in detail by Claudio on Friday. So we go now to the predictions about theta dependence from an analytical point of view. Well, the first kind of predictions, since we know that theta dependence is related to classical solutions of the Yang-Mills equations, so to instantons and anti-instantons, is if we can make any predictions by integrating around such classical solutions. So this is something that is possible from a perturbative point of view. Basically, one can make a perturbative computation and compute what is the one instanton contribution to the path integral. And the result is that the contribution from one instanton is weighted in the path integral by this factor, the exponential of minus 8 pi squared divided by g squared of rho. So this rho is the size of the instanton. I mean, instantons and anti-instantons are characterized by several parameters, and one parameter is the instanton size, rho. So basically, this g squared is the square of the gauge coupling computed at the instanton scale rho. So this prediction comes from perturbative computation. It is a one instanton computation. So first of all, it assumes that instantons are diluted objects, so that do not influence each other. And it is also a perturbative computation. So it is expected to work well by asymptotic freedom only for small instantons. So where rho is small compared to the QCD scale. And the prediction is that that the instantons are suppressed by this exponential factor, which is smaller and smaller as the instanton scale becomes smaller, because the coupling goes to 0. However, we know that perturbation theory is expected to break down for large instantons. And indeed, the same computation, I mean, this semi-classical computation permits to obtain a prediction about the distribution in size of instantons. And the prediction is the following. So this is the density of instantons, the space-time density of instantons, and also the distribution in size of instantons. And as you can see, this distribution for NC 3 or larger, also for NC equal 2, is divergent in the large rho limit. So we have this infrared divergence predicting a large number of instantons, but this divergence, of course, is regularized by itself, because for large instantons, this prediction we know that is unreliable, because we are not in the perturbative regime. So in principle, the prediction by this model, which is known as the dilute instanton gas approximation, is expected to break down because of the presence of large instantons. Anyway, we might have phases in Yang-Mills theories which are characterized by some infrared cutoff, where the instanton size is limited. And one relevant example is QCD at finite temperature. So QCD at finite temperature sets an infrared cutoff to the theory, which is represented by the temperature itself. And so in principle, we can say that for a large enough temperature where only instantons with a very small size survive, this dilute instanton gas approximation might be reliable. these are more details on the dilute instanton gas approximation. Basically, within this approximation, you can make an exact computation of the dependence of the free energy density on the theta parameter. And the essential ingredient is that the instantons and anti-instantons are Poisson distributed, so they are independent of each other. And the final result that you get is that the theta-dependent part of the free energy density is proportional to the topological susceptibility times this 1 minus cos theta. And this is a very precise prediction for the all these coefficients that I showed you before in the Taylor expansion. I mean, you can predict this B2 to be minus 1 over 12 and so on, which can be carefully checked by lattice simulations. Furthermore, there is also a prediction for the temperature dependence of the topological susceptibility, which is the following. This will be discussed more in detail by Claudio on Friday, because it is related to axion phenomenology. Now, one feature of the dilute instanton gas approximation is to predict that actually in the large N limit, because the large N limit in Yang-Mills theory is achieved by sending the 't Hooft coupling lambda, which is the product of B squared times the number of colors, by keeping this lambda parameter fixed. When you go to NC infinity, it means that the one instanton weight, the single instanton weight, is expected to go to 0. It means that according to the dilute instanton gas approximation, the topological activity should go exactly to 0 in the large NC limit. And in particular, also the topological susceptibility should go exactly to 0. Now, this is in contrast with the Witten-Veneziano formula, which requires a finite value for the topological susceptibility in the limit of a large number of colors. So, so this is in some sense in contrast with this phenomenological prediction from the eta prime mass. And the standard argument by Edward Witten to circumvent this problem is to assume that the natural variable in the large N limit is not theta itself, but theta over NC. Now, this idea comes natural when you look at the Yang-Mills Lagrangian formulated with a theta parameter. So the theta parameter appears in this way in the Lagrangian. So it appears when you put in evidence the 't Hooft coupling, the theta parameter appears divided by the number of colors. But I mean, the important fact is under this assumption, I mean, that the relevant parameter for theta dependence in the limit of large N is theta over NC, is that the free energy density is expected to scale as the number of colors squared, which is a natural expectation because the number of degrees of freedom in a large N is proportional to NC squared. The number of gluons is proportional to NC squared, times this function, which is a function of this bar theta, which is theta over NC. Now, if you consider the Taylor expansion of this expression, it comes out that the quadratic term, because of the cancellation of NC squared with the first NC squared in the second order term, stays finite. Okay, so the Witten argument essentially is that if you require a finite value for the topological susceptibility in the large N limit, then indeed you expect that the free energy density must be a function of theta over N. And now if you consider back the Taylor expansion of f of theta as a function of theta, and you match the powers, you discover that the topological susceptibility is expected to be finite, to stay finite in larger limit. And the corrections, so the quartic and so on corrections to the purely quadratic dependence are expected to be suppressed as powers of the number of colors. So this P2 goes as 1 over c squared and so on. That means that in larger limit, the topological charge distribution is expected to be a purely Gaussian function. I mean, only the quadratic term survives. And the free energy density as a function of theta is expected to be a purely quadratic function, but periodic at the same time. That means a multi-branched function which with a discontinuity in the derivative at theta equal pi, or odd multiples of theta equal pi, which corresponds to first order phase transition, which are expected in the larger limit. And these are actually quantum phase transition, because we are at 0 temperature still in this case. Now, further observations about this are the following. So one may ask whether this dependence on theta over n instead of theta itself is like having some effective degrees of freedom, which are not instantons and anti-instantons, but objects with a fractional topological charge, of non-integer charge, but charge 1 over the number of colors. So I will show you later that this picture is not exactly consistent with what we find by lattice simulations. Then another point is that when we consider QCD-like theories like the CPN models, one can go further with the Lagrange predictions. I mean, the Lagrange predictions that I showed you now for Yang-Mills theories are semi-quantitative. I mean, we can predict some general behavior of the Taylor expansion coefficients, but we don't know the prefactors. In this model, CPN models, you can be more quantitative also for the prefactors, and that makes these models interesting also for comparison with lattice simulations. I will not have time to discuss in details these models in my talk. So finally, even if I will not discuss results from full QCD simulations, let me just mention briefly that when you go to full QCD, so when you introduce fermions, and in particular light fermions, you can move the theta term to the light quark sector, and in this way you can have very precise predictions for theta dependence, so about the topological susceptibility and also about the quartic corrections and so on, which can be confronted with the lattice QCD results. And I think this will also be discussed by Claudio on Friday. So, any question by now?
I think you can go ahead.
Okay.
Yes.
So now I will move to a review of lattice results. Let me make an outline of what are the most interesting questions about theta dependence. Now, of course, we would like to check Lagrange predictions, so the Witten-Veneziano formula and the scaling of these B2 coefficients that I mentioned before. Then, in general, we expect that at large enough temperature, the D-routine certain gas approximation should become reliable. So one question is, what is this scale of temperatures, and whether there is any relation with the confinement transition that we know to take place for Yang-Mills theories. Finally, another question that I will discuss is how theta itself influences the QCD phase diagram. So, is there any influence of theta on the confinement transition itself? Then, of course, there are other very important issues that I will not discuss. so prediction for axion cosmology, and non-perturbative predictions for the electric dipole moment of the neutron that will be discussed in many other talks, and in particular also by Dina in the talk after the coffee break. Let me just sketch a first introduction to lattice QCD simulations. So very briefly, the elementary variables that we have in lattice QCD simulations are the parallel transporters between lattice sites, which communicate the different rotation of the gauge group that we have in different sites because of the local gauge freedom. The fermion fields live on lattice sites, and their presence is encoded in the fermion matrix, in the fermion determinant. And when we consider finite temperature formulation of the theory, we have periodic boundary conditions for gauge fields and antiperiodic for fermion fields in the temporal Euclidean temporal direction. And essentially, the temperature is related to the inverse of this Euclidean temporal extension. There are many technical issues that we should discuss in detail when considering the study of topology and theta dependence from lattice QCD simulation. So this is just a list. I mean, to discuss in detail, we would need maybe another talk. First of all, there are normalization issues. So the topological charge is defined in the continuum, and the topology, since it is related to the homotopy class of gauge fields, is essentially a continuum property of gauge fields. So when you study this on a discrete spacetime, you may face different various difficulties. So you have to choose some discretization of topological charge, either gluonic or fermionic. But in any case, you have to take care of the fact that the topological charge might be non-integer, and that you should take care of normalizations, like for any other quantum operator that you consider in your quantum field theory. There are several techniques that you can make use to face this problem, like computing the normalizations or making use of smoothing techniques. I mean, trying to move the gauge fields toward their minima, where the topology is better defined. And for this reason, there are several ways to study topology on the lattice. And one of my purposes in the next slide is to show you that all these methods actually give you consistent results. Then you have to take care about the continuum limit extrapolation, and this continuum limit extrapolation might be more difficult when you introduce light fermions, but I will not discuss this in more details. One difficulty is when you want to access information about higher order cumulants. This is because it is like trying to compute the deviations from a Gaussian distribution in a distribution which is almost Gaussian. So it is a noisy measurements, which might be difficult. And finally, there are also algorithmic issues. I mean, because of the topology-related issue, the algorithm which updates the gauge configurations when you get very close to the continuum limit might face difficulties in changing topological sector. Okay, so you have something which is known as topological freezing. So the algorithm becomes unergodic. And furthermore, there might be a situation, especially at high temperature, where the topological susceptibility is suppressed, where the expectation value of Q squared might be very small. And so essentially the difficulty is that of sampling very rare events. Okay, but let me go to the to the results. So let me start by results that we know about the topological susceptibility in SU3 pure gauge theory. Well, the reason why I start from this topic is this because by now these have been studied in plenty of lattice work, also by different methods. I mean, methods which directly study the properties of gauge fields, so which employ a gauge field discretization or topological charge, or by methods which look at the spectrum of the Dirac operator, so methods based on fermion zero modes, methods which try to subtract normalizations, or methods with smooth configurations in order to extract their global topology. And the results that I show here in this picture are a collection of different methods. I mean, obtained over the years, starting from this 1997 paper, which was actually the subject of my PhD thesis, so a very long time ago. Then down to very recent determinations obtained by spectral projectors. So one essential common characteristic of all these results is that all these results have been extrapolated to the continuum limit. As you can see, they are in a pretty good agreement among each other. If you make a fit to a constant value, you obtain a perfectly consistent value of the chi-squared. Another thing that you can see is that the common value is larger than the 180 MeV that you expect from the Witte-Veneziano formula according to the eta prime mass. Now remember that this 180 MeV for the fourth root of the topological susceptibility is expected in the large N limit. So here we are in SU3. So it is not clear that it should be asymptotic already for NC = 3. Now the answer is reported in the next slide. Actually, the topological susceptibility has been computed for several values of the number of colors. And in this picture, I report the square root of the topological susceptibility. This is multiplied by this parameter R0, which is called the Sommer parameter, which is a common way to determine the absolute scale, the absolute physical scale of your lattice spacing. But I report the 180 MeV for comparison by this dashed line. And here on the horizontal axis, there is the inverse of the number of colors squared. So basically 0 is the large N limit. And you can pretty see that all the values indeed seem to converge from NC = 3, 4, and 6 to the value which is expected by the Witte-Veneziano formula. So results at zero temperature, these are lattice results obtained at zero temperature, as in pretty agreement with the Witte-Veneziano formula. So one question is, do we have the large N behavior of F theta is what we expect according to the Dirac-Nielsen gas approximation, or what do we expect according to the Witte ansatz, where the scaling variable is theta over n? Now, of course, we have a topological susceptibility which is finite. This is not compatible with the Dirac-Nielsen gas approximation. Anyway, it is interesting to compare also this fact with the computation of these B2 coefficients, which is expected to scale as 1 over NC squared according to the Witte ansatz. Instead, it is expected to be 1 over 12 according to the Dirac-Nielsen gas approximation. So this coefficient B2, which is related to the 4th order cumulants of the topological charge distribution, has been computed since 2002, and results for SU3 are reported in this picture. As you can see, over the years, the lattice determinations have become more and more precise. Now we have a precision at the level of 5%. And it has also been computed for different values of the number of colors. So in this picture, you can find the results for this B2 for n equal 3, 4, and 6. And this scaling, this expected scaling according to the Witten ansatz as 1 over n squared has been very nicely verified on the lattice results. And so we have verified that B2 behaves like this B2 bar divided by n squared. And the value of these coefficients appearing in the numerator is this minus 0.193 with an error of 10. I will come later to the value of this coefficient in a few slides. So next question, what about finite temperature? Remember that the general expectation is that at high enough temperature, since the theory becomes perturbative, the d-root instanton gas approximation should become reliable. So we should have some change of behavior of the theory as we move to finite temperature. So the question is whether this change of regime in theta dependence coincides or not with the confinement transition. So whether there is any relation between this transition in theta dependence and the standard, the confinement transition taking place in SUN Yang-Mills theories. Now, also in this case, we have answers coming from many years ago and also more recent determinations. So the answer coming from, let me say, 20, 30 years ago is that there is a drop of the topological susceptibility around the transition, and this drop becomes more and more sharp as we move to large n. So as we move to the large n limit. So this drop by itself, so the fact that the topological susceptibility drops to 0 after the confinement transition is not by itself a proof that we are moving to the d-root instanton gas regime. It's not strictly compelling. We have examples like in two-dimensional CPN models where the topological susceptibility goes to 0, but in the large n limit, but the system is not a d-root instanton gas. Anyway, a definite proof comes from measuring also these quartic corrections, so from the measurement of the B2 coefficients, and we have evidence that indeed there is a sharp drop at the transition here. 0 locates the confinement transition, so this small t is the reduced temperature, so T minus Tc divided by Tc. And one can see that shortly after the confinement transition, the value of these B2 coefficients, which is suppressed as 1 over n squared at low temperature, moves to the value which is expected for a d-root instanton gas. So to this minus 1 over 12. And also the behavior of the topological susceptibility as a function of temperature has been carefully checked to be consistent with the power law behavior in T with the correct power predicted by the d-root instanton gas approximation. So putting all together, the emerging picture for SUN Yang-Mills theory is the following. So let me start from the confinement region and then trying to move back to the confinement region. So from Tc on, so in the high temperature regime, and shortly after the confinement transition, we have that topological excitations indeed behave as a d-root gas of non-interacting objects, where theta dependence is proportional to 1 minus the cosine of theta. Well, there are some corrections right above Tc, but this correction disappears very rapidly. Now, this scenario changes completely when we move into the confined region, where the large M predictions based on the width and ansatz sets in, and we have that the free energy is a function of theta over n. And so let me say that sometimes, from a theoretical point of view, this is interpreted in terms of the appearance in the low temperature phase of Yang-Mills theories of topological objects which have a topological charge 1 over n instead of an integer topological charge. And these objects are usually called instanton quarks. Now, let me say that the results that I just showed you prove that the situation is more complex than that. It's not so easy. Or at least that if these objects exist, they are not weakly interacting. The reason is that assuming a gas of non-interacting instanton quarks, one would expect a theta dependence 1 minus cos theta over n, and that will give us a B2 coefficients, which is minus 1 over 12 divided by n squared. 1 over 12 is this number. The number that we obtain from numerical computations is instead this number, which is more than twice the expectation. So this means that these objects must be at least strongly interacting among themselves. So corrections must be significant. No, now, unfortunately, I ran out of time. There are just 10 minutes left. So maybe I will just show you the results about a different question. The different question is, we have seen that the different phases of QCD, confined or deconfined, have a strong influence on the theta dependence of the theory. Now, the other question is whether theta itself can affect the phase structure of the theory. So whether having a non-zero theta may move the confinement transition in some way, either to lower temperatures or to higher temperatures. Now let me sketch briefly what are the analytical predictions about that and what are the numerical results. And this is the last part of my talk. Now, basically, the analytical prediction is that indeed one expects the transition to move to lower temperatures as you switch on a theta parameter. And the reason is the following, very briefly. We know that the confinement transition for n equal 3 or larger is first order. So we have a latent heat. It means that we have two different phases with two different free energy density sheets which cross exactly at the phase transition point. So what happens when you introduce a non-zero theta parameter? It happens that both free energy sheets will shift by a quantity which is proportional to the topological susceptibility. Now, since the topological susceptibility is different in the two phases, it means that the two sheets will shift differently, and so the crossing point will move. And that means that the confinement transition will move as you switch on theta. Okay, this is very briefly what we expect to happen. This is an exact argument in the limit of a large number of colors, and I cannot discuss in details the details, but the expectation based on measurement about the topological susceptibility and about the latent heat that we have in the large n limit is the following. I mean, we expect a quadratic dependence of Tc theta over Tc0 on theta with a coefficient which is related to the ratio between the topological susceptibility at zero temperature and the latent heat of the theory, which is the following. Also, this coefficient is expected to scale as 1 over nc squared. Now, from a point of view of lattice determination, the issue is more complicated. I will skip many details here, but basically what you can do, since you cannot perform direct simulations at non-zero theta, is to introduce an imaginary theta parameter in the same way that you do when you consider QCD as finite baryon chemical potential, where you can try to obtain information from simulations at imaginary chemical potential. And so basically what one can do, you can also adopt reweighting techniques. I mean, this has been done in this paper, obtaining consistent results. But basically, the idea is to introduce a finite imaginary theta, look at how the temperature moves as a function of this imaginary theta parameter, and then exploit analytic continuation to turn these results into a prediction for the critical temperature as a function of a real theta parameter. Let me go briefly to the results. So this is how the transition moves, located by looking at the susceptibility of the Polyakov loop, which is the order parameter for the confinement transition in pure gauge theories, as a function of the imaginary theta. So basically, this is Tc over of theta over Tc of 0 as a function of theta squared for negative values of theta. And from there, you can compute the slope and then extrapolate to the continuum limit, obtaining finally a prediction for this coefficient R of theta, which turns out to be of the same order of magnitude as expected from the large N argument that I showed you before, but not exactly that, because we are for NC, these simulations are done for NC equal 3. Okay, these results can be checked, have been checked actually also by other means, by reweighting, so by making simulations at 0 theta and then reweighting to real theta, obtaining consistent results. And basically, let me go to the concluding slide, which is the following, which is a conjectured phase diagram at non-zero theta. I mean, the expectation is from these results that the confinement transition indeed lowers as you switch on theta. So that means that a non-zero theta enhances the onset of the confinement. So the critical temperature lowers. So confinement of color is made less likely as you introduce a non-zero theta. But anyway, notice that the drop of Tc is not so large, at least at the quadratic level. I mean, the expectation is that as you reach theta equal pi, the critical temperature is lowered by 20%. So the confined phase does not disappear when you switch on a non-zero theta. It just, I mean, according to this lattice result, which can be checked also by other results from a different group. So you have a drop of the confinement transition, but you still have confinement at 0 temperature. Okay, so this is actually my last slide, summarizing that numerical results from lattice QCD simulations provide a very clear picture, which is consistent with available expectations and which suggests a strict relation between the confinement and the change of theta dependence. And moreover, theta itself enhances the onset of the confinement. Now, let me just mention a few interesting topics that I did not have time to cover in this talk. I mean, the fact that this numerical study of theta dependence can be even more interesting from a numerical point of view in QCD-like theories like the two-dimensional CPN models, where you have more precise and quantitative analytical predictions. And let me just mention a series of papers over the last few years that you can look for this issue. and also a paper which is appearing on the archive tomorrow morning, where we have some definite evidence that indeed for n equal 2 in these models, the topological settability has a divergence. And finally, another interesting topic is another way to look at the close relation between theta dependence and the confinement and center symmetry realization in Yang-Mills theories, which is obtained by looking at trace deformed Yang-Mills theories. And also in this case, I just report a series of interesting papers over the last few years. And that's all. Thank you.
Thanks, Massimo. Questions? So, Skyler?
Yeah, thanks, Massimo, for a really interesting talk. I have two kind of naive questions. The first one is, you mentioned very early on that one can add a vacuum angle in the same way to an abelian gauge theory. And of course, it's well known that QED is not CP violating. And my understanding of this was that there are no structure factors in the gauge theory that correspond to non-commutation of the gauge group generators. Is that an equivalent statement, or were you pointing at something more subtle?
For the abelian theory, you mean?
Yes.
No, I was just meaning that, I mean, in the abelian theory, if you consider a gauge configuration with a non-zero winning number, you need a configuration with an infinite action. I mean, with the fields not vanishing at infinity. You don't have semi-classical solutions with a non-zero winning number.
I see. So this is not to do with the interaction, the self-interaction of the gauge bosons, but with the boundary conditions of the theory itself.
Exactly. Yes.
Okay.
Yeah, exactly. Yes.
Okay. Perfect. Thank you. And then my second question is a little bit more schematic. So obviously with theta, it's challenging to make contact to experiment when we don't yet have an experiment that measures something finite. But are there lattice calculations, for example, in few body hadronic parity violation, where there is a chance to trace the symmetry violating mechanisms and confirm that calculations near a physical point are agreeing between theory and experiment, and maybe you could then use the same tools to study theta?
So you mean whether you can obtain theta dependence predictions from hadronic processes?
Well, I'm interested if hadronic processes or anything else provide some kind of way to cross-check the calculations that you're now doing for theta.
Well, of course, yeah. I mean, you have a first example is with the Veneziano formula, but also, for instance, you can relate another quantity, which is the I did not mention in this talk, the chi prime, which is the derivative of the when you consider topological settability as a function of the q squared of the transferred momentum, and you take its derivative. This is also a quantity which is related to hadronic processes, and so of course there are many connections that can obtain, and I cannot. Yeah, the answer is yes. I mean, but there are several examples that we'll discuss. Yes.
Okay. I mean, from the experimental point of view, we're always kind of thinking of this in terms of effective field theory, where there are many different symmetry violations that get collected into one observable. And then if there's a theoretical tool for tracing what has come from where, then that's extremely useful, but you now need some way to disentangle.
Mm-hmm.
Okay. Thank you.
So, any more questions? Please, let me.
Thank you. So in the continuum limit for these toroidal backgrounds, periodic boundary conditions, the topology is fixed, and essentially one would, instead of having to rely on the numerical fluctuations of the topology, one would have to sum over the different topological sectors. Now, I could imagine that if I could run such a simulation, or could make such a computation with a fixed topology in the continuum limit or very close to the continuum limit where topology freezes, then I could measure what is the mass of the eta prime on the lattice. I could also look at the topological susceptibility by looking at the subvolume, and I would find that in the subvolume, the susceptibility is just fixed, is fluctuating, whereas in the entire volume, it would be fluctuating. And I mean, okay, I can't do such a simulation, so to some extent it is a speculation, but I could imagine that these results of such a computation would not differ from the results that you have presented. But then in such a theory, in a single topological sector and the continuum limit, the theory doesn't know anything about theta. So how clear is the connection between the expansion in cumulants from that perspective and the dependence of the partition function on theta, which after all then opens the connection with neutron EDM?
Okay. So indeed, I mean, you mean so indefinite volume limit? Of course, you can consider, as you said, a single fixed topological sector, and you would obtain information about the fluctuations in the subvolumes. Well, in any case, I mean, what we are obtaining in that case is something which is related to the 2-point functions of the topological charge density, which is related to the, you can obtain from that the eta prime mass and other quantities like the topological susceptibility. One point where this method is phased, or at least is not so easy to use, is when you want to compute the higher order cumulants. I mean, when you move to the higher order cumulants, you will need to compute 4-point functions of the topological charge density and so on, which from a numerical point of view is more and more difficult. I mean, this is why I did not consider, or we do not consider this this possibility, I mean, of making numerical simulations down to the continuum limit at fixed topological sector. But in any case, for the topological susceptibility, it is fine and to make to obtain the same results in this way. Now, regarding the how the theta dependence is back in this case. Well, I think that everything can be related to the fact that finally the zero, I mean the expansion, the Taylor expansion coefficients of this theta dependence can be related to the cumulants themselves. So basically, anything that you can determine and measure at 0 theta can be related to what you expect at non-zero theta. So in some way, this is the way you can recover the dependence on theta. Of course, this is something that you that works well only around theta equals 0, and assuming that the dependence on theta is analytical. I mean, for sure you can obtain predictions for theta close to pi in this way. I don't know if I answered to your question.
Yeah, maybe a quick comment, and maybe we should go to a topic break.
Yeah, so it's a bit of a pity because this is probably something we should indeed continue in a coffee break, which we don't have together. But
Yeah.
maybe to frame it in a more simple question. So would you expect that if I were able to run a simulation in the continuum limit of a fixed topological sector, and then I measure the chiral susceptibility in a subvolume, would you expect that you get the same result as in the present approach with a discrete lattice? And no matter what the answer to this is, would there be any pathologies in such a theory with a fixed topological sector in the continuum?
So Massimo, will you be here at 4:30?
I fear no.
Okay, but we can still, still discuss this. I mean, it's a nice question.
No. I mean, the point is subtle. I mean, I think that it depends on how you take the infinite volume limit, and I expect that. I
guess also the focus is the fixed topological sector, right?
Yes, of course, but of course it depends on how you take the fixed topological sector at the infinite volume limit at fixed topological sector. So my impression is that my answer is that you will obtain the correct result because the correlation, the 2-point correlation function becomes independent of the topological sector if you take the infinite volume limit appropriately. But of course, there can be some subtlety about how you take the infinite volume limit. So it is not completely trivial, but my answer is that you will obtain the correct answer, yes, if you look at the subvolume.
Okay, so we can discuss this later. So okay, so thanks, Massimo.